In the previous video, we looked at the most common form of the first-order ordinary differential equations. It can be written as mxy dx plus nxy dy equals to 0. In this video, we'll look at a specific case of the first-order ODE called Bernoulli equation. Bernoulli equation can be written as y prime plus px y equals to rx. If we rewrite y prime as dy over dx, then the equation above can be written as dy over dx plus pxy equals to rx. Multiply dx on both sides, we'll have dy plus pxy dx equals to rx dx. Then move the rx dx to the left-hand side, we'll have an expression like this. That is pxy minus rx plus dy is equal to 0. If we compare this expression to the most general form, mxy is the same as pxy minus rx. nxy is simply just 1. Let's rewrite the Bernoulli equation in the original form. There are two scenarios. In the first case, when rx is equal to 0, we call this equation homogeneous linear ODE. In the second case, when rx is not equal to 0, we call this equation non-homogeneous linear ODE. In this video, we'll look at the homogeneous linear ODE, and in the next video, we'll look at the non-homogeneous case. For homogeneous linear ODE, y prime plus pxy is equal to 0. We want to write y as a function of x. What we do is to repeat what we just did in the previous page, writing y prime as dy over dx. Multiply dx on both sides of this equation. We will have dy plus pxy dx equals to 0. Rearrange what we have here. Then we can write dy is equal to minus pxy dx. Divide y on both sides of this equation. We'll have 1 over y dy is equal to minus px dx. Integrate both sides of this equation. The left-hand side of this equation becomes log y, and the right-hand side remains the same. Since we're doing integration, we need to plus a constant here. The constant is c star. Take exponential on both sides of this equation. You will have this expression. Then take out the c star from the exponential sign. Assign exponential c star as c. We have our general solution for the homogeneous case. Y is equal to c multiplied by exponential minus integrate px dx. In the next video, we'll derive the solution for the non-homogeneous linear ODE and apply the solution to a real math example.